So hi all. So welcome back to discussion on quantum optics. So in this small video, I will be discussing about the coherence and the different types of coherence within a light source. Okay. Now this word coherence is very familiar to us because from higher secondary onwards we are hearing this word, the coherence source, coherence, and so on. So what is actually meant by coherence? So the coherence actually gives the measure of the phase relationship between or phase relationship at, of a light at two different points. Or okay, so coherence, it is a measure of it's a measure of phase relationship of light at two different points. So what is meant by that? What is meant by this phase relationship? Okay, so suppose we have an electric field. So classically, the electric field at some position r and t, we can write in this form: is E0, the amplitude, then cos of k dot r minus omega t plus phi. So this k dot r minus omega t plus phi is called phase. Okay, so this is the phase. Okay, so this phase I can denote by symbol delta. So this is a phase at the location r at a time t is k dot r minus omega t plus phi. Okay, now if you take two different position, suppose the position is r1 and another position is r2 at the same time. Okay, it need not be the same time, it can be a different time as well. So t1, t2. Then you find this k dot. So this become okay, k dot r1 minus omega t1. So this k dot r2 minus omega t2. So this the phase constant become phi. Okay. So if there is any relationship between these deltas, so delta of R1 T1 and delta of R2 T2, if there is any relationship between them, then we say it is coherent. Okay, so maybe so these values may be equal, or this value may be this difference may be some constant. So okay, so if somehow if there is any relationship between these two deltas, then we say technically we say uh, these 2 points are coherent. Okay, now for coherence, as far as the light is concerned, we can define two types of coherence. One is called the spatial coherence, and another one is called temporal coherence. Okay, we can see what is by these two. So first we can check what is by spatial coherence. Okay, so in the spatial coherence, basically we'll discuss or we'll study the phase relationship between the 2 points, which is perpendicular to the direction of propagation. So along the line, perpendicular direction of propagation. Suppose if the light is moving towards right, okay, so consider some wave is moving towards right. Then if you take 2 points, okay, so this is the direction of propagation. So if you take 2 points, which is along the line perpendicular to the direction of propagation. Okay, so this will be along the wavefront. So along the wavefront, if you take these 2 points, okay, so if there is any definite phase relationship between these 2 points, then we say they are spatially coherent. So if the source is spatially coherent, then up to that distance, the wavefront would be flat. Okay, so the spatial coherence or the distance up to which the light is spatially coherent, then the wavefront will remain flat up to that distance. Okay. Now the distance over which the light is spatially coherent, we call such coherence as um, the lateral coherence, no, lateral coherence length. Okay, so suppose up to this distance, so okay, so only up to this distance, the wave is coherent, and over above this distance, if the wave is not coherent, then this distance we will call lateral coherence length. So up to the lateral coherence length, the wavefront will remain flat. Okay, now the spatial coherence decides directionality of light. Okay, so this decides directionality, and it depends upon the size of the source. Okay, so these are the two factors which remain the spatial coherence. Okay, and how we can check the spatial coherence? The one simplest way to measure the spatial coherence or the lateral coherence length is we can perform a Young's double slit experiment. So in case of Young's double slit experiment, there will be two slits separated by some distance S1, S2, and slit separation is D. Okay, so if you increase this slit separation, then what would happen if the light which is reaching at S1 and S2 are not coherent, we will not get any fringe pattern. So usually we'll get fringe pattern over here if the source at S1 and S2 are coherent or spatially coherent, then only we'll get fringe pattern. So if you increase this separation, if you increase the separation between S1 and S2, then after certain distance, then the source need not be spatially coherent. The S1 and S2 source or S1 S2 points need not be spatially coherent, and the fringe would be invisible or fringe not visible here after certain distance. Okay, so distance over which the fringe is visible, we can say that is the lateral coherence length. Okay, so if this is the lateral coherence length, then if you take some other point here, that's a point 1, point 2, point 3. The point 1 and point 3 would not be coherent. Okay, but whereas the point 1 and 2 would be coherent. So that is the idea about the spatial coherence. So in case of spatial coherence, if there is any definite phase relationship between the points perpendicular to along the line perpendicular to direction of propagation, then we say they are spatially coherent. Spatial coherence depending upon the size of the source, and this spatial coherence, the length of spatial coherence decides directionality. So if you want to direct the beam to one particular point, then up to that much distance, it must be spatially coherent. Otherwise, it would diverge. Okay, so you may get this kind of light. So the light would diverge if they're not coherent. Okay, so here, so if you take spherical wavefront, okay, its a spatial coherence length would be very small. If you take the plane wavefront, the spatial coherence length would be large. Okay, the spatial coherence length means the lateral coherence length. Okay, and very simple experiment to measure the lateral coherence length is just employ, just use the Young's double setup. So if you have a source here and the light coming from the source, and if you have two slit S1 and S2, if S1 and S2 is within the lateral coherence length, you will get fringe pattern. If D or if the separation between S1 and S2 is greater than this lateral coherence length, we can turn by symbol D, then you will not get any fringe pattern. So if D is less than LS, we'll get fringe. If D is greater than LS, then no French possibility. Okay, so that's the idea about spatial coherence. Now, what about temporal coherence? So in the case of temporal coherence, you'll be checking the spatial correlation between the 2 points along the direction of propagation. Suppose you have some light is propagating along this direction, and if you take 2 points, suppose this point and this point, so these 2 points is along the direction of propagation. So if these 2 points are coherent, then we'll call it this temporal coherence. And the distance over which, okay, so up to what distance? So the distance over which the light is coherent is called the coherence length, and usually denoted by symbol LC. Okay, now why it is called temporal coherence? The reason is if you look at this location, so suppose this location had denoted by symbol R, and some time here is time t. Okay, now the light which is over here will reach the same location after some time. So if this t is this time, then if there is up to LC, if it is temporally coherent, then at the same location at the time t plus LC by C, the second point will reach here. Okay, so this is the first point, the second point. The second point will reach the location of the first point after certain time. Okay, so that is why the term temporal or the time which is come over here, because so if the light reaching at the same location at two different instant are phase correlated, then they call temporal coherence. Okay, I will repeat. If the light reaching at the same location, then those lights are said to be temporally coherent. So sorry for interruptions. There is some connection issue in between. Okay, now this LC by C is called the coherence time. So this XLC is the maximum distance over which the light is coherent. So coherence time identifies by tau is equal to LC by C, or the coherence length LC is equal to C into tau. Okay, now how we can measure this temporal coherence, or how we can measure this coherence length? So this LC is usually called coherence length. So one of the simple way to measure the coherence length is a Michelson-Morley experiment or Michelson-Morley setup. Michelson-Morley interferometer. Okay, so in case of Michelson-Morley interferometer, you'll have one source, and the light coming over from the source will be divided into two using a partially reflecting mirror. So some portion would be transmitted, some portion would be reflected, and they will return after reflecting from a mirror. Okay, now the light which is coming over here has traveled different distances. So obviously the light which is reaching over here might have emitted from the source at two different times. Okay, suppose if the light or if the horizontal length is large compared to the vertical length, then the light coming from the horizontal might have come out from the source at earlier time than the light which is come from the top mirror. Okay, so I think you have got the idea. So from okay, now if the separation or if the arm separation, the horizontal and vertical arm separation is very different, or if it is very large, if it is larger than compared to the coherence length, then you will not get any fringe pattern. Okay, so we can have some notation. So suppose this is okay, better we can have the partially reflecting mirror P M1 M2. So if PM2 minus PM1, okay, its magnitude. So if its magnitude is less than the coherence length, we'll get fringe. Otherwise, no fringe pattern. Okay, because here the light coming from two different instants are interfering here. Okay, so I think it is clear to you. Okay, so the temporal coherence or the coherence length can be directly measured by using the Michelson-Morley interferometer setup, and the coherence length is equal to C into tau, and where tau is called the coherence time. It's the time over which the light is coherent. Okay, now from the theory of optics, we know that the coherence time is proportional to or inversely proportional to the bandwidth. It's inversely proportional to bandwidth. So therefore, the coherence time is equal to 1 by delta nu. Okay. Now we know that C is nu into lambda. So therefore, if you take derivative delta, so delta C would be 0. So nu into delta lambda plus lambda into delta nu would be 0. So delta nu would be equal to nu into delta lambda by lambda. So that we can substitute over here. So tau, which is 1 by delta nu, is equal to 1 by nu delta lambda times lambda. Now what is nu? Nu is C by lambda. So it's equal to lambda square C into delta lambda. Now we can calculate the coherence length. So coherence length is C into tau. So that would be equal to lambda square by delta lambda. So the coherence length we can measure from this particular expression. Okay, so if you know the spreading wavelength of a light source, then the coherence length is lambda square by delta lambda. So lambda gives the mean wavelength of the light source, and delta lambda is the spreading wavelength. Okay, so if the spreading wavelength is very small, then the coherence length would be very large. Okay, so we can just estimate the coherence length of the different sources. Okay, so we have the normal light source. Okay, the sunlight or visible source. So visible light, the wavelength ranging from 400 to 700 nanometer. So delta lambda is approximately 300 nanometer. And what is the average wavelength? The average wavelength is around 550 nanometer. So we can calculate the coherence length for visible light. So that would be 550 square divided by 300. and we can show that it is approximately equal to 1000 nanometer. So for the visible light, the coherence length is around 1000 nanometer. Now, if you take sodium, the sodium we know that it has two dominant wavelength, 589 and 589.6 nanometer. So for sodium, the wavelength is 589 to 589.6 nanometer. So then for the lambda, average is 589.3 nanometer, and delta lambda is 0.6 nanometer. We can calculate the coherence length, and here the coherence length is seems to be very large compared to the visible light, because the visible light is only 1000 nanometer, where the delta lambda is 300 nanometers. Delta lambda is large. Now in case of sodium, the delta lambda is very small, just 0.6 nanometer only, and hence the coherence length we are getting the range of 578 micrometer. So this is very much large compared to the coherence length of the normal visible light. Okay, so we can use this kind of sodium light for the interference experiment, for the Michelson-Morley interference experiment, interferometer experiment. The sodium light is good. We can get, or we can control the separation between the mirrors, and if it is within this 500 micrometer, we'll obviously get the interference pattern. Okay, so if that separation, okay, so you have to remember this separation. So if this separation is partially silvered mirror to M1, partially silvered mirror to M2, if that's difference in separation should be less than the coherence length. So this is achievable. So this separation is achievable. So we can get interference pattern using sodium light, whereas it is not possible to get the interference pattern in Michelson interferometer using the usual visible light. Now, when you are going from sodium to mercury, again, the coherence length increases. So for mercury, it is in the order of 1.2 centimeter. And if you go for laser beam, okay, so a typical laser will have delta nu, approximately 1 kilohertz, and the coherence length will come in the order of few kilometers. So it comes in the order of 300 kilometers. So it is very easy to achieve the interference experiment using laser rather than the sodium, because sodium is we have to control within the few micrometers, so that is the one problem. And for laser, there is no issue. The coherence length is very large, so we can easily get the interference. So that is why in the most of the new Michelson interferometer equipments is coming with an attached laser beam rather than the sodium source, because there the possibility of getting interference is very easy. Okay, so with these remarks, I'm going to stop today's discussion. So today we have just introduced what is meant by coherence. So the coherence is basically a measure of the phase relationship. The phase relationship in the sense that the difference of the phases at two different locations or at two different time. So if if there is any definite phase relationship, okay, definite phase relationship means it may have the same phase, or it may have some constant phase difference. So that is what is meant by definite phase relationship. So the difference should not be random. Okay, so if you take two phases, okay, so maybe delta 1 minus delta 2, if if this is a function of time, if it is a function of time, then there is no phase relationship. That is, if this difference changes with time, then we say that there is no phase relationship. If it is a constant, then we say that, okay, there is some definite phase relationship. Okay, so there can be, we can measure the phase relationship perpendicular to the direction of propagation and along the direction of propagation. If you are measuring the phase relationship perpendicular direction of propagation, it is called the spatial coherence, the spatial coherence, and spatial coherence decides the directionality, and it's also depending upon the size of the source and the distance up to which the wave is spatially coherent is called lateral coherence length, and we can measure this lateral coherence length using a Young's double slit setup, and that we have explained here. And after that, we discussed about temporal coherence. So temporal coherence, if there is any definite phase relationship along the direction of propagation of light, then it's called a temporal coherence. And I've explained why it is called temporal coherence, because the same light will reach the same location after a certain time. Okay, so the time. Okay, we can also say that the time over which the light is coherent. So that is why it's called temporal coherence. And the temporal coherence or coherence length, we have a quantitative definition for temporal coherence length. It's reciprocal to the bandwidth of the source. Okay, so if the bandwidth is small, the coherence time would be large, or coherence length would be large. And we have estimated the coherence length of different light sources. And we also said that how we can measure the coherence length. Okay, we can use the Michelson-Morley setup to measure the coherence length. Okay, or to demonstrate these temporal coherence. Okay, so that's up to now. And the next class we'll discuss about the correlation and the correlation functions. So thanks for watching this video. Thank you.